essentially what I'm using this relation to set up my matrix. Essentially what I did was, to the right hand side I have M here now, and this would be M over here. So that's what I'm saying. So I said, put a table like this. If n equals 0, m equals 1, I have a square root of 1, of course. So it's 1. Now, what is more interesting, let's move on. If m equals 0, n equals 1, then element is 0. Make sense? Okay, so in other words, if m equals 0, n equals 1. So if m equals 0, m equals 1, and this has to be 0. Makes sense? Because they're orthogonal, right? So this has to be 0. So in other words, if you swap them, this was 0, so this would be 0. So there's no other options. So we get 2 elements. Now let's keep on going, because this makes things a whole lot more interesting. If n equals 1, n equals 1, you get 0. Make sense? Everybody's good? Can I get thumb up? Everybody give me thumb up. Now, if n equals 2, n equals 1, the element will square root 2. So that will make sense. So if n equals 3, n equals 2, you get square root 3. Get it better? Get it better? So you could do this whole time. So essentially what you will get this matrix. Did you see? You will get this matrix. So the top one is 0 for you, all 0. And the lower half matrix will be square root of 1, square root 2, and keep on going 3, and 4, just a very long matrix, it's infinite basically. And so that's why last time when I showed you a matrix, you start with this. It's a whole lot simpler when you look at this matrix. And then you see all the upper part, all zeros. The lower part is just determined by this guys, like this. Okay. So that's why I thought about this when I was answering your question and said, wow, I did not do a good job when I draw these diagrams over there. It's not that easy. So now on the computer screen, you can see it's much simpler. Okay, now you will have homework. Yes, go ahead, question.
So this might be a dumb question, but what's n represent within this? Because isn't it like 2 different states? So
n here is a quantum number. If n here is a quantum number, so n here, n represents quantum number.
yeah.
Quantum number. Yeah.
What's
So
n?
m is also a quantum number, but when I set up the matrix, m is also both. They both are quantum numbers. It's just when I represented the operator A or A dagger into the matrix, I must have 2 indices. Otherwise, you cannot have a matrix with 1 index. You have 2 indexes. 1 index determined by this n, another determined by this m. So then you have 2 indexes. So you could say I have the column index, let's call it n here. This column index n, and the row index is m. Then I have these index set up. So essentially what I did was I represented this A dagger operator in the basis function of the eigenfunction of harmonic oscillator, so that I have these matrix elements. You see all the diagonal terms all zeros. All the upper part will be all zeros. And then those part will be square root 1 here, and then the adjacent square root 2, square root 3, square root 4, and keep on going like this.
So m and n represent energy states, but
yes,
not explicitly the energy states.
Exactly. Until you specify what actual states you are interested in. This just gave you a tool to do whatever you want. For instance, if I'm interested in, let's say, n equals 10, like this. If I'm interested in n equals 10, then yes, you can use this matrix. You basically cut off at 10. Cut off at 10, then you do whatever you need to do. So this is, it just gave you a tool. So this is the A dagger, like this. A dagger is giving you this matrix. And the A itself is also giving you similar matrix, and that's your homework. And then when you have A dagger, these matrices, so we can do a whole bunch of things. That's the job for these operators. And I hope this extra explanation helps you, right? Get it better. So that's called a representation. Essentially, we use these as basis function to represent an operator, which is abstract. We don't like these abstract things. And then we have a matrix which you can handle on this. Okay. Any other questions, students? Any other questions? Sounds good? Sounds good? Okay. I think that's all that I have here. Great. So we do not need to use the zoom now. So I'm going to exit the zoom. And so today what we're going to do, we're going to just basically continue our last portion of the study. This will be the last section of our class. Last time what we did was we essentially used the Schrodinger picture to represent these states. And these are a small error which I'm going to point this out. Let me show you. There's when we print it out, there's an could you guys go to page 75? It is in example 3. If you in the book, example 3. Example 3. The last 3 equations, you will see delta px squared, and then you have a whole bunch of things like this. And there is a term f1 squared. I missed 3. It should be correct to 3 f1, and in the book. So this is the delta px. In the equation we have in the book we have f1 squared. It should be 3 f1 squared. I'm not sure whether you are able to. Do you find it at 75?
Like the first.
Yes, it says similarly. Let me show you.
This part right here.
Yes, just like this here.
Yeah.
Yeah, just this one here. It should be 3. Yeah. Please add 3 there, and add another 3. Yeah. It's like what I did. 3, 3. 3 lines. These 3 all have 3s. Yeah. Next, f. So all these 3, and then next line, delta x parenthesis square, delta p x parenthesis square, and this also has to be changed to 3f. And the last expression also is 3f1. So we have to correct them. Last equation, delta px also have to 3 1f. Otherwise, it's incorrect. So these are, we discovered when my colleagues was teaching and discovered there is an error, so you make sure you do put it there. Aisha, did you find the equation there? Yeah. Okay, very good. So this is the correction that I want to mention. Okay, so, and now, today what we're going to do is we'll have some times for you. Well, we're about 2 minutes. All right, anyway, so about 2 minutes, but we will show you a quick picture for the section. This is newer section, hold on, section 5. Yes, so this is section 5. So here, which we call Heisenberg picture, and mainly will be direct Heisenberg equation of motion. So this direct Heisenberg equation of motion. Now, I purposely written in this way, and just want to make sure it was derived by Dirac, not derived by Heisenberg. And Dirac was so modest, and he tried to use the Heisenberg's name and to identify these equations, but it's derived by Dirac. So this is the way Dirac. He's extremely modest person, and was kind of a really important contribution to physics. Since we won't be able to cover all of them, but I want to show you a big picture on this before we get move on to the next the quiz part. So So here's a big picture. The bigger picture is the following. Schrodinger equation, which I'm going to use S to represent. This is called Schrodinger picture. Heisenberg picture. They represent things are differently. In the Schrodinger picture, the wave function I am represented by phi sub s. That's a Schrodinger picture. At t equal 0, it's different from its wave function at t not equal 0. So in the Schrodinger picture, the wave function is different. This is the Schrodinger Schrodinger equation. The operator, which I'm going to use the letter A to representing that in the Schrodinger picture, so also use a subscript S to representing that. In the Schrodinger picture, the operator at t equals 0 is going to equal operator at t not equal 0. I'm not sure whether I confuse you guys. In other words, the wave function time dependent. Operator is not time dependent. Why the Heisenberg picture is swapped to these two. Its wave function is not time dependent. Its wave function is not time dependent. So wave function is a time independent in the Schrodinger picture, but its operator is. So operator, I use the letter subscript H representing that. So the operator at time equals 0 or not equals 0, they are different. So that is a big picture. In other words, if you remember these things, so this is using the Schrodinger equation, time-dependent Schrodinger equation. And this one here is a time-dependent Heisenberg equation of motion. Equation of motion. We don't call it Schrodinger equation or Heisenberg equation. We call it Heisenberg equation of motion. The reason was that this is a physical measurement of the quantity, like a velocity, momentum, position. So that's why we just remember the name different. We have a motion of motion, the name. Schrodinger equation of a wave function, if you want, of a wave function. And motion means the physical quantities. Motion of physical quantity. For instance, velocity, position, and momentum, all these will be physical quantities, which we'll use. So that will be put off until Friday. So Friday we're going to discuss these ones. All right, so we're going to stop this now. We're going to have your quiz and